Hey there, awesome physics students. Let's talk about electric field lines. Now, electric field lines are a way to extend our ideas that we talked about with electric fields, but they're so powerful because you can use them to conceptually understand a situation just by making a simple drawing or interpreting a simple drawing. So let's get started in understanding what these are about. Now, we know the electric field is going to tell us about the force on a hypothetical positive charge at every point in space. That's why it's called a field. It's a vector at every point in space. And we typically only draw a few representative electric field vectors to get an idea of what the electric field looks like. The idea with lines is to extend this just a little bit, and it makes it so much more useful. So if I have a positive charge here, it's going to also feel a repulsive force. And the idea here is that, hey, why don't we just join these lines together, these electric field vectors. So I will join them all together in a line of electric field, and I can just draw an arrow on there to indicate the direction of that electric field vector. Similar with this, I can just draw a line to infinity or from infinity to indicate what's going on here. Let me just draw a few more of these. So they're going to be like this, like that, outwards at every point. Okay, now there's a few key ideas that you can even just see by looking at this. We know that the electric field will be stronger if you're closer because the force is stronger, right? The electric field is the force divided by the amount of charge that would be there if you put it there. As I get closer, these field lines get closer too. And as I get farther apart, the field lines spread farther apart. So that's one of the main ideas in electric field lines, is that the density of lines, or the number of lines, or how the spacing of the lines, tells you about the force. Here, the force is big because the lines are spaced close together. Here, or here, or here, the lines are far apart, so the electric field is a lot lower. We can use this idea in a bit more precise fashion if we look at different charges here. So we know, let's say this charge is a negative charge. Well, it is a negative charge. And so the electric field vector is going to point inwards, actually, because electric field lines are going to point towards the negative charge. Okay, so let me just draw 4 electric field lines that are coming, and I don't want to extend those to infinity just yet. Now I want some way to represent the fact that when I'm over here close to this this positive 2q charge, that the electric field is bigger over here than it is over here because this is a bigger charge, and this the size of that charge should win, right? So to do that, I need to represent the electric field lines coming out of this just as well. These are going to come outwards, just like that one, because it's positive. What I do to solve this is I just draw twice the number of field lines as I do for the smaller charge. This is twice as much charge, therefore I draw twice the number of field lines as I do on the smaller charge, right? I have 4 lines here. I need 8 lines here. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 lines. And if I extend these to plus and minus infinity, well, this line will just join up with this line. This line here will join up with this line, like that. This line will join up with this line like that. These lines don't have any, I mean, this one might curl around the earth and join up with this one, but these lines just go to infinity and they don't join up with anything. And you can see automatically here, without even trying very hard, that if I'm here, the density of field lines here is a lot lower than if I'm over here. The lines are closer together. And so that takes that into account. So that's another rule of electric field lines, is that the number of electric field lines going into or out of a charge is proportional to the amount of charge that is. So twice the charge, twice the field lines. The other important point is that the electric field lines always go into negative charge and out of positive charge. And so that gives us another rule. Electric field lines must begin and end at charges only. They cannot just start out of thin air and then end in thin air. They have to terminate or begin on charges themselves. And so with this scheme, I can just see, based on the number of field lines, there's 4 here, there's 8 here, I don't even have to tell you the size of the charge. I could just figure out, oh, there's twice as many field lines, therefore there's twice as much charge. And I know the direction. The direction tells me whether these are positive or negative, so I don't even have to write what the charges are. Finally, there's this very important example with the two charged plates. So one's a positively charged plate and then a negatively charged plate. And these are parallel to each other. So think of these as sheets of metal that are separated with a distance here. And one has negative charge on it and one has positive charge on it. I just follow some of the rules I've established here. I start on a positive charge, I end on a negative charge. And so my field lines will just look like this. And if I just follow these rudimentary laws that rules for field lines that I've created, I can see immediately that the electric field strength does not change as I move across from the positive side to the negative side, because the lines don't get closer together or farther apart. And all I needed to know was that lines begin at positive charges and end at negative charges, and that is the only thing they can do. And the number of lines emanating from a charge is proportional to the amount of that charge. And the density of those lines indicates the strength of the electric field. Where the lines are close together, the electric field is big. Where the lines are far apart, the electric field is small.